Good morning, everybody. Happy Thursday. Everyone's wide awake, ready to do math. And by everybody, I mean myself. Okay. So, let's go ahead and talk. Let's get started here. One of our last lessons for the year. So, for our warm-up, find the determinant of P. Okay, so remember these vertical bars here, kind of like we're used to using them as absolute value. That's just another way that we can write, the determinant of P. Either one of these notations is perfectly fine. Doesn't matter. Okay, so we have a formula for this. All right, so first we look at this top corner. And then we imagine if we crossed out this row, crossed out this column, then these four numbers, so -1, -1, 2, 1. And then now there's a minus sign, that's just part of the formula, is that the next is minus. Then we look at this next top number, which is 1. And then we imagine cross out that column and row. What's left? So these four numbers, 1, -1, 1, 1. And then now lastly, we look at this third number in that top row. So this is just 1. Since it says +1, so we just have +1. The only time that we need to worry about that the formula has a negative is just in this spot right here. So even though this is a +1, the formula has a negative sign there. Okay, and then same thing, cross out the row and column. So we have these four numbers left. 1, -1, 1, 2. Okay, so now each of these 2x2 determinants, so we have a formula for 2x2 determinants. And that is just multiply the main diagonal, so -1 times 1 is -1, minus 2 times -1, which would be -2, so -1 plus 2. Okay, minus 1 times, now this determinant, 1 times 1 is 1, minus 1 times -1 would be -1, so that'll turn into a plus, so 1 plus 1. And then plus 1 times 1 times 2 is 2, minus 1 times -1 is -1, so that would be 2 plus 1. Okay, so again, another situation where all of these, even though the 2x2 determinant formula has a minus here, since that second number was negative for each one, then it turns into a plus sign. All right, now it's just simplifying more. Negative 1 plus 2 is 1. 1 plus 1 is 2. 2 plus 1 is 3. So 2 minus 2 plus 3 is 3. So the determinant, 3. What can we conclude from this? So specifically, we know the determinant is not 0, which means this matrix is not singular. What that means is this matrix does have an inverse. Right? We've kind of talked about different ways we can find an inverse, but even without actually finding it, we know that just the existence of this inverse matrix for P. Right, if we had gotten a determinant that is equal to 0, we would say, no, this does not have an inverse. This matrix does not have an inverse. Hope you're comfortable with this determinant formula. We're going to use it a lot today. A lot, for sure. Okay, so let's go through and talk about Cramer's rule. All right, so Cramer's rule is it's a way of solving 3-variable systems. Okay, so for example, if I need to solve for x, y, z, well, what we've done before is, well, we've done these by hand, first of all, which is annoying. Just like doing substitution and elimination. We've also used matrices to get reduced row echelon form, Gauss-Jordan elimination, also annoying. So here we have another way, which is called Cramer's rule, so that x is equal to dx divided by d, dy divided by d, dz divided by d. Okay. So what do each of these things represent? Okay, well, this just capital D here is just the determinant of the matrix. Okay. No big deal. But what about like the dx or the d sub, the dy or the dz? What is that? I have that question over here. It is the matrix. Well, I'm not going to write it out. There's not a good way to write it. I'll show you. But it means it's the matrix where you replace the x column or the y column or the z column, depending on which one. You replace that matrix with, or that column with the answer column. Right, if that makes it, that doesn't make sense saying it, but I'll show you what I mean there. Okay, so let's Cramer's rule to solve the system. Okay. So first, let me transform this into a matrix. So 2, 1, 1, 1, negative 1, negative 1, 1, 2, 1. Okay. Oops, let me. Okay, so remember that capital D represents just the determinant of this. So I just looked at my stuff over here on the left side of the equation, right? 2, 1, 1, 1, negative 1, negative 1, 1, negative 1, negative 1, 1, 2, 1, 1, 2, 1. Okay, now what is the determinant of this matrix? Well, there's a reason I chose that for our warm-up, because if you'll look, this is exactly that matrix. 2, 1, 1, 1, negative 1, negative 1, 1, 2, 1. All right, so we already know this determinant is 3. All right. So now we need to go through and figure out what is the dx, what is the dy, what is the dz. So, give me a purple. So what I'm going to do is, so again, this is another determinant. Instead of, so I'm going to leave these second column and the third column the same. 1, negative 1, 2, 1, negative 1, 1. Okay, but I'm going to change, instead of having 2, 1, 1, 2, 1, 1 for this first column, the x column, I'm going to replace that with the answer column. I don't know what you want to describe it as, but the column that has just the equals from the right side of the matrix. So I'm going to replace that with 3, 0, 0. Okay, so we just took this, basically this original matrix, but instead of having 2, 1, 1, I replaced this because it's the x. This is dx, so we replace the x column with whatever the values are from the right side of each equation. Okay. Now we're just doing our determinant formula. Okay, so first number 3. Remove the row and column. We'd have these 4 values left. Minus, because the determinant formula says minus, then I move over positive 1 times the determinant of, so if I get rid of this column and this row, so 0, negative 1, 0, 1, plus positive 1, and if I imagine that I get rid of that row and that column, so I'd have these 4 values, so 0, negative 1, 0, 2. And so we're just calculating 2 by 2 determinants now. So 3 times negative 1 times 1 is negative 1 minus negative 2, so negative 1 minus negative 2, that's 1. Okay, minus 1 times 0 times 1 is 0, minus 0 times negative 1 is 0, so 0 minus 0 is 0. Great, that's easy. Plus 0 times 2 is 0, minus 0 times negative 1, so again, 0 minus 0. That's awesome. So this just equals 3. 3 minus 0 minus, or 3 minus 0 plus 0. Great, 3. Okay, so now I know that this dx here is 3. So to actually solve what is x, so we use dx divided by d. So dx we figured out is 3. D from our original determinant is also 3. And 3 divided by 3 is 1. So in this system, the x value is 1. Good to know. Okay, so now let's move on to y. So I want dy. So what do? I'm taking my original matrix. So 2, 1, 1, 1, negative 1, 1. Okay. So these numbers 2, 1, 1, 1, negative 1. These are the same things that come from this column and this column. 2, 1, 1, 1, negative 1. But now, since we are doing dy, instead of keeping this y column the same, now I'm going to do the same thing I did. I'm going to replace the y column with these values from the right side of the equation, 3, 0, 0. Now I'll calculate the determinant of this. Okay, hopefully you can get pretty quick at recognizing the pattern of doing determinant of 3 by 3 matrix. Right, 2, 3, and 1 just come from these numbers across the top. Remember, the middle number changes sign because there's a minus sign here in the formula. And then what goes inside of these 2 by 2 determinants is just whatever this number is. If you take out that column and that row, there should be 4 numbers left. That's what goes in here. Right? Or if I move on to the 3, if I take out this column and this row, I'll have 1, negative 1, 1, and 1 left. Right? Etc. Okay. And then same thing for calculating the determinants. Should get pretty good at this. This would be 0 minus 0. Great, that's 0. Okay, minus 3. 1 minus negative 1. So that would be 1 plus 1 is 2. 0 minus 0, 0. So 0 minus 6 plus 0 is minus 6. So the y value we can get by doing dy divided by d. So dy is negative 6. D is positive 3. So the y value is negative 2. Okay, last one. Let's just do z. dz. So now since this is z, we're going to replace the z column with like the answer value. So the x column will stay how it should. The y column will stay how it should. But now the z column, right? So now our x column stayed the same, our y column stayed the same, but now the z column will get replaced with these values, 3, 0, 0. Okay, and now formula. Right, 2 by 2 determinants, 0 minus 0, 0. 0 minus 0, 0. That's awesome. Plus 3, 2 minus negative 1. So 2 plus 1, 3. So this would be 0 minus 0 plus 9. So 9. Okay, so the z value should be dz divided by d. So that's positive 9 divided by capital D, the original determinant, which is 3. So 9 divided by 3 is 3. So we've solved for x, we've solved for y, we solved for z, and we get that our final answer is, wait, not negative 1. X was positive 1, right? Yeah, x positive 1, y negative 2, z 3. 1 and negative 2, 3. We solve the system. X, Y, Z. The thing that's also pretty nifty about Cramer's rule is we can separately solve for each variable. So if you're solving by hand using like a substitution elimination, or if you're solving using Gauss-Jordan elimination to get it into reduced row echelon form, it's kind of all a total package, right? If you want to solve for x, then you're going to have to go through and solve for y and z as well. All right, you don't have a lot of control over like which variable you're solving for. But Cramer's rule is excellent for, you know, maybe depending on the problem, maybe I don't care what x and y are. Maybe I just need to figure out what z is. Maybe that's the only variable I actually need to solve for, or that's what the question asks about. Or maybe it just asks about the x value, or maybe it just asks about the y value. Well, then I don't want to waste my time doing work to solve for x and y or whatever if I don't need to. Right? So Cramer's rule is excellent for, like, maybe if I just needed to solve for y, well, then I would only need to do this section of work. Right? Because this has nothing to do with what x is, or has nothing to do with what z is. Right? I can separately solve for this without worrying about the other stuff. Right? So I know overall it's still a lot of work. If I'm solving for x, y, and z, then yeah, it's still a lot. But if I just want to pick out a specific variable, then it's not as much at all. Okay, and I think on the, I think Cramer's rule is on the additional the AFA for matrices, and it just asks you solve for y, so you just need to do the y stuff or z or whatever. Okay, so let's look at another one. So let's say, let's practice what that looks like. So not to solve the system. Let's say to solve. Here, look. I'll do some masterful Photoshop. Wow. Let's say to solve for, I don't know, does anybody care? X, Y, or Z, it doesn't matter. Someone pick one. I don't care. X, Y, or Z. All right, Y it is. So use Cramer's rule to solve for Y. Okay, and you can't even tell this is all just perfectly normal. Indistinguishable. I didn't edit this at all. Okay, so first up, we need to find D. Okay, so D is just the determinant of the original 3x3 values of the matrix. So 2, 1, 1, 1, negative 1, 4, 1, 2, negative 2. Been talking too much. All right, so we use our determinant formula. This minus sign is here just because it's part of the formula. Even though this is positive 1, we turn that into a minus on that second term only. Okay, so we just need to figure out what each of these 2x2 determinants is. So this would be positive 2 minus 8, negative 6. Negative 2 minus 4, also negative 6. 2 minus negative 1, positive 3. So negative 12 plus 6 plus 3. So negative 6 plus 3, negative 3. Okay, so that capital D is negative 3. And now, since we are trying to solve for y, now what I'm going to go through and do is find dy. So that means the x column will stay the same, and the z column will stay the same. Right, but since we're trying to solve for y, so we're doing dy, the y column will not stay the same. The y column is now going to get replaced with the right side of the equation, those values, 1, 0, 3. Okay, now it's just 3x3 determinant. So do your thing where you eliminate the rows and columns to get those 2x2s. Minus 1, 1, 4, 1, negative 2. Plus 1, 1, 0, 1, 3. Okay, so let's just figure out what these are. So this would be 0 minus 12, so negative 12. Negative 2 minus 4, negative 6. 3 minus 0 would be 3. So negative 24 plus 6 plus 3. Which would be negative 15. Okay, great. So I have everything I need. So the y value should just be dy divided by d. Right, so that just comes from our formula here, right? dy divided by d. dy we just decided was negative 15. Capital D from earlier is negative 3. So negative 15 divided by negative 3 is 5. So the y value is 5. All right, we didn't even need to figure out what x or z was. We could just specifically focus on the y to solve for what it should be. Right? And again, that's what that looks like on the AFA as well. It'll just give you a system and it'll just say just solve for one variable. So even though as long as you're good with 3x3, as long as you're good with determinants, then I think this method is much easier. Rather than trying to go through and do the Gauss-Jordan elimination, you know, to get the to try to get it into reduced row echelon form. There's like all those steps. Or rather than doing solving a system by hand of just doing substitution and elimination, all right, that's a mess too. So this is still, you know, there's still a lot of tiny room for error in terms of mishandling a negative or adding or subtracting or something small like that. But overall, I think this is nicer if I want to just, especially if I just want to solve for one variable. Maybe even nicer in general. Maybe even if I want to solve for all x, y, and z, I would probably still rather do this than do Gauss-Jordan elimination. I think Cramer's rule is easier, straight up. That's just me. We could do it for x, we could do it for z as well. I don't know. If you want me to do that, I can do that. Anybody want to see x or z? It's just the same, again, it's just the same thing. I would say do x and z just on your own to practice. You already know what d is, so all you would need to go through is find dx and find dz in order to solve for x and z. All right, so you can do dx over d to solve for x, dz over d to solve for z. Okay. Any questions about anything overall? Okay. Then hope you have a great rest of your day. Great weekend. I will see you back on Monday. We'll talk more. We're going to talk about the final. All right, we have a final exam still. So we're going to talk about that, what that's going to look like. I'm going to give you some review stuff that you can look at just to practice. And that'll be that. I don't plan to give you a performance task for matrices. I don't want to give you another thing to have to worry about, so we'll just have that final exam. If you like really want a performance task, like individually, I could give that to you if you really want it. But if you're happy with, maybe, and that's just maybe if you like want more performance tasks for a better chance to raise your grade. I don't know. I can do that. You can let me know. I can give you one if you specifically want one. But otherwise, we'll have that final exam. It's technically worth 20% of your grade, but it'll still be like open note and stuff like that. So I don't know. Again, we'll talk more on Monday, but just be aware. And I will see you guys on Monday. All right. Have fun. How long is the exam? I don't know yet exactly. Not super long. I'll give you guys a long time to do it, but it won't be a super long exam. If we were taking it in class, it would be like 50 questions or something, but it absolutely will not be anything like that. So, but I'll tell you more on Monday. All right.